Howdy, Professor. This is our proposal presentation for our MXET-375 Applied Dynamics final project. We went ahead and titled our project a sixth degree of freedom robotic gripper. We are group one of section 903, and my name is Christian Guerrero.
I'm Jacob Stowe.
And I am Miguel Angel Lopez. Okay, for our proposal links, we don't currently have the YouTube link uploaded, nor do we have the Google Drive uploaded. Obviously, because we're recording it, as you can see. But after the recording, we will upload it and update our slides to include both of those links so that you can have access to both. In the event that our YouTube link does fail for whatever reason, you will be able to still access it through our Google Drive because we will have an uploaded copy. For our project description, we are building a system that consists of two robotic fingers, each with three rotational joints, allowing for 3 degrees of freedom per finger. Each finger is composed of rigid links, as displayed by these black rectangles on our schematic that are connected by joints with purple circles, forming a segmented structure similar to a claw or finger. Tension spring is attached externally across all joints to passively restore the finger to an extended position, denoted by the red on our drawing right here. And a string will be anchored to the fingertip, being routed through the inner side of each segment and connected to a DC motor at the base. This DC motor will rotate, causing the string to be pulled in or reeled in, and the finger to curl in against spring tension for actuation. Our DC motors are denoted by these blue figures down here. And as you can see, as one motor reels it in, the other should because they are both copies of each other. We will focus on the dotted segmented part first, and then just copy it over.
So our plan of execution was divided into disciplines across the product. The mechanical aspect was a task to me, and that begins with designing and creating a CAD model for the singular freedom for a singular finger for a 3 degree of freedom in Fusion 360. After that, we will then go into looking for a spring to use as the restoring force for when the finger does curl. After all that is done, a 3D print will be done to implement everything and to analyze and make sure that everything works perfectly for the project.
For the electrical system, the first part, obviously we need those motors to connect to the strings. I don't think we need a full motor. We need more of a servo with only a limited amount of movement because if we move too much, it will just crunch the finger. So we need to keep it moving only about that much, however much the string pulls to get that much. Um, And then obviously, once we've decided on a servo, we need to make sure also when we're deciding on the servo that it has sufficient torque to actually clench the finger and do it. Once we've decided on the servo, we'll then need to connect it to a microcontroller based control system, which will interface with the motor drivers. So we'll have a little computer that controls the motors. Probably independently. So, well, one stays rigid, the other one might stay stiff, or vice versa. Um, and then obviously that whole system needs to be programmed. That'll be dependent on the microcontroller that we use, what it is programmed in. But essentially, all the program needs to do is spin the motor a certain amount to clench the finger a certain amount.
And I will be focusing on the simulation aspect of the project. That will include building a dynamic model of a single 3 degree of freedom finger using Simulink and SimScape, similar to what was used in the 5 degree of freedom robot from previous labs. Once I build that single model, I can then duplicate it for the overall system. I will then include the effects of the single external spring and motor-driven string in a dynamic simulation to evaluate the system's response. System response being relative position and torque. I will then run simulations to analyze the finger's motion, as was mentioned before, and the required motor torque and overall behavior under various input conditions.
So similar uh to the last slide, we distributed the work kind of based on what people are good at. That means Christian's doing the CAD modeling, mechanical assembly, selecting the springs for the correct amount of tension or compression, and then the actual physical testing once the electrical system is integrated. That depends on me doing the electrical system. I need to select the correct motor or servo, figure out how to mount it to our system, and then once it's connected, maybe not even once it connected, just pulling the string manually might work. Test that that motion actually works. And then obviously with the motor as well, we need to be able to control that motor with the microcontroller, which is another one of my tasks, and how much it controls. Next, we also need to do the simulation, which is done by Miguel. He's going to simulate one finger, and then we can duplicate that to two fingers. We need to integrate the spring and motor force modeling, and then run testing and simulations and document the results, and then connect those two for a more accurate simulation.
So the timeline was developed to where we could have the mechanical aspect of the project done about halfway through the project timeline, so that then we could have about the same amount of time to implement the electrical and control parts in order for it to work. The simulation spans over the whole project, and that's simply just to give us enough time to get the simulation perfect and make sure that it works properly to gather the simulated data to compare with our experimental data. Each of these they are tasked to individual owners. However, it is a group project, so we will collaborate together to make sure that we're all hands-on and understand the overall concept and how every discipline interconnects with each other for presentation to Professor Guru.
Okay, so our expected outcomes, we obviously want a functioning prototype of a two-finger 6-degree of freedom robotic gripper, passing spring extension and motor-driven curling, as you had seen in previous slides, what that should look like. We then want a validated dynamics simulation model created in MATLAB's Simscape or simulation, or Simscape or Simulink that accurately predicts the motion and forces of the finger system. We will then require, or we would rather output a demonstration of the motor control over finger curvature, enabling basic grasping and object manipulation. And this will then give us insights into the mechanical behavior and control dynamics of tendon-driven, under-actuated robotic fingers that can then be used for further projects, similar to what the 5-degree of freedom robot had done. And that is it.
Thank you, Professor, and we look forward to beginning this project.
Gigam, Professor.
Gigam.
Gigam.